Welcome back, students, to our Chemistry 2620 video notes. In this video, we're going to talk about amino acids. So when we start talking about amino acids are just a difunctional compound that's essentially a monomer. And these monomers will connect to one another and make a polymer that we call a protein. So these have both an amino group and a carboxylic acid group. When the amino group and the carboxylic acid group end up reacting and come together, they make this bond here. This bond is your peptide bond. It's essentially the bond that makes this structure an amide, right, between a carbon of a carbonyl and a nitrogen. So peptide bonds are a bond that connects to, two amino acids, right? And amino acids, when they connect and they form that protein, is just a huge polyamide, right? So it's a polymer with amide bonds, and it's just in the context of proteins that we take that amide bond and call it a peptide bond instead. So with some more nomenclature, before you get to proteins, there's a stepping stone there, right? Peptides are a short chain of amino acids. So if you're talking about one amino acid, that's a monomer, right? And that's just an amino acid. If you're talking about a couple, maybe, 10 linked together, then you're talking about a peptide. If you're talking about a significant number connected together, that would be considered a protein. So when we start looking at amino acids, there is one carbon in particular that really matters, and it's this one here that I'm highlighting in blue. The amino acid is special in the sense that there's always one carbon between the carbon of the carbonyl, which would be this one, and the nitrogen of the amino group. So this carbon here is called your alpha carbon, and it's the one carbon between the amine and the carboxylic acid group. So you've probably heard of all 20 amino acids that are naturally occurring, and you probably also know that what they have in common is this part. And what changes is the identity of the R group, which is also called a side chain. We do not memorize the structure of amino acids. We save the specific structures and their abbreviations for biochemistry. So if you want to see this table of the 20 amino acids associated with their abbreviation, please feel free. It is not something that you will need to memorize. You will want to be able to know which ones, based upon the structure, would be considered acidic or basic, because that's some of the stuff that we're going to talk about now. So we're going to look at pH and pKa and talk about those amino acids and how they're going to behave, and also how their side chains are going to behave. So when we start looking at amino acids at very low pH, both of these groups, the COOH and the NH2, are going to be protonated. So remember, low pH is very acidic, right? So at pH of 1, you're taking the carboxylic acid and you're absolutely making sure that it's acidic or acidified and has been protonated. And the NH2, which is a base, when that base encounters acid, right? This is going to be protonated. So at pH of 1, you're going to have both of those components be protonated. And what we're going to find is that each group has their own individual pKa. So what you're going to find is that in general, the first pKa, so the pKa1, the pKa1 is going to be associated with the carboxylic acid pKa, and the pKa2 is going to be associated with the amino's pKa. Keeping in mind that, remember, the amino's pKa only has a pKa if you're talking about the protonated part, right? This doesn't have a pKa because it's not an acid, right? That's a base. So in general, what you're going to see is that your carboxylic acid group is going to have a pKa in the range of 2 to 3. And the protonated amino group is going to have a pKa in the range of about 9 to 10, right? And these are abouts because if you'll look at this table over here, you see, one's a little bit greater than 10, one's a little bit greater than 10. These are a little bit less than 2, so we're in the about range. And then notice how only some of these have side chains with pKa's. So not every single one of these has a side chain that's going to have its own pKa. And we're going to talk about that as we start to look at the possible side chains. So let's start getting into what that pKa means for an amino acid. So if we look at something like alanine, which is drawn off to the side over here for you. So when we look at alanine here, I've written out the pKa's for you specifically. So when we see these pKa's, what these pKa's mean is if we have a solution that has the same pH as the pKa, then half of your groups will be protonated and half of that group will be unprotonated. So what I mean by that is at pH of 2.34, the pKa for COOH is 2.34. So this hydrogen can come off at 2.34. So at pH, oh, for heaven's sakes, at pH of 2.34, what you're going to find is that 50% of your COOH is COOH and 50% is COO minus. So half is protonated and the other half is deprotonated. Below that pH of 2.34, your solution is very acidic. And so if your solution is very acidic, then everything should be protonated. So your COOH will be 100% protonated. Above pH of 2.34, you now have a more basic solution than this pKa is illustrating that is required for that H to come off. And so above the pH of 2.34, your carboxylic acid group is going to be a carboxylate anion, and it's going to be deprotonated. Deprotonated. So when you're looking at this and you're thinking, well, what about the NH3 group? That's a great question. So let's talk about that NH3 group. The NH3 group has a pKa of 9.69. So what that means is when our pH is equivalent to the pKa, we're always going to have that 50-50 protonated and deprotonated. So 50-50 mixture of protonated and deprotonated. If we have a solution where the pH is less than this pKa, then what that means is the solution is acidic enough, and don't get confused when I say acidic enough, because you can be like, well, this is a basic solution. Yes, I know, but it is acidic enough to the point where we can't pull off that proton yet. So that stays protonated. But as soon as you're above 9.69, then your amino group becomes deprotonated completely. And you're probably at home thinking, why are we doing this? And that's a really wonderful question, because what we want to be able to do is understand the trends of pKa and pH to the point where we can determine what an amino acid is going to look like at physiological pH. So let's just draw a little scale off to the side over here. I find that this helps people. So if this is my oh man, what do I want this to be? I guess it could be my pH scale. If my pH goes here from 0 to who cares what, 14. Let's say here is 2.34 and here is 9.69. So what you're going to find is, if we look on this side, this side will be our amino side. Let's do that, and that'll be easier, I think. This will be our amino side, and this will be our carboxylic acid side. So between 0 and 2.34, you're going to have this be protonated. Between 2.34 and up to here, your carboxylic acid is going to be deprotonated. Right at 2.34, it's going to be half and half. So if we look at the amino group, between 9.69 and 0, your amino group will be protonated. Above 9.69, it'll be deprotonated. And right here at 9.69, half will be protonated and half will be deprotonated. And so this usually helps people figure out the answer to the next question, which is on the following page. So let's go to that following page. So let's assume physiological pH is right around 7.2. The question becomes, what will the amino acid look like at physiological pH? And I drew it here for you. And what I want you to do is pause and go back to the top of the prior page that you just took notes on and see why you're going to have a deprotonated COOH, right? So COO minus, and a protonated amino, because this is going to be very important for your future exam questions. When you end up having something that has both a negative and a positive charge in the same species, that's called a zwitterion. So your zwitterion is a species in which a positive and negative are in the same molecule. To form a net neutral molecule. And remember, net means overall. So let's start thinking about that amino acid and physiological pH. Will this amino acid be soluble in water, or will it be soluble in organic solvents like, ether or dichloromethane? So take a moment, maybe pause yourself and think about that. So if you paused yourself, maybe you recognized that your COO minus and your NH3 plus are both ions. And like dissolves like. What that means is polar things dissolve polar things, and nonpolar things dissolve nonpolar things. Because your amino acid has two charges in it, the amino acid is polar. And water is also polar. So they're going to dissolve in each other. You've seen this in general chemistry before when you saw things like how vodka doesn't form two layers because ethanol is polar and water is polar. But you've also seen how oil, vegetable oil, and water do form layers because vegetable oil is a non-polar hydrocarbon with all carbon-carbon or carbon-hydrogen bonds, which are both non-polar. And so that does not dissolve in water. So let's look at that amino acid and decide if it's going to behave as an acid or a base. So if we have an amino acid that gets stuck with some HA, our general acid, and we look at our two options here, we see that this COOH already is protonated, and our NH2 here is not. And so our NH2, which I believe I drew too many electrons on there, has the capability of behaving like a base and pulling off a proton. So the amine can act as a base. Whereas if we put a base in, our general base B, we'll see that carboxylic acid proton and remove that. So our carboxylic acid behaves as an acid. So when a molecule can behave both as an acid and a base, we call this amphoteric. And an amino acid can do just that. So you might be saying, well, why would we worry about this inside of the body? Well, that's a good question. You'll worry about that when you get to biochemistry. But outside of the body, we can definitely make amino acids, and we can put them through chemical reactions. And so this is just an important thing to remember as we start looking at some properties of amino acids. So we have one more thing to do in this video, and that's talk about the isoelectric point. The isoelectric point is a pH, and when we look at this pH, it's the pH at which the molecule is net neutral, so contains no electrical charge, right? So it's net neutral. So when the amino acid has only two groups, the pi, which is the isoelectric point, right? So that's the abbreviation for isoelectric point, is very easy to calculate. All you do is you take your pKa's, you add them up, and you divide by 2. So when your pH is at the pi, then your sample is perfectly balanced and contains no electrical charge, right? It's net neutral. Whereas if we end up having a amino acid that has a side chain, then it takes a little bit more effort. So when we consider something like lysine, lysine has a basic side chain. So notice how here's your carboxylic acid, here's your amino group, here's your alpha carbon, and here's your basic side chain. And glutamic acid has an acidic side chain. So here's your carboxylic acid, here's your amino group, here's your alpha carbon, and then this is your acidic side chain. So what you do when you're trying to calculate the PI for the compounds or the amino acids that have an acidic or a basic side chain is you find the two groups that are the same and you calculate the average between their pKa's. So what I mean when I say the same is, for example, in lysine, you have an amino side chain, and so you choose the pKa of the NH3. You take those and you average them. Whereas in glutamic acid, you have a carboxylic acid side chain. So you find your carboxylic acid side chain pKa, you find your carboxylic acid's pKa, and you calculate the PI. So I think that's probably enough for that video here. We will end our pH-PI discussion with this, and we'll come back in another video to wrap up the rest of the chapter. As always, thank you for your attention. This is Katoni signing out.